let me just say a few words of introduction for the theme very quickly. In particular, this is theme 1 of the 4 themes that will be discussed here during the Power of Synergy workshop. This particular theme and the discussion that will follow this afternoon revolve around the question of large-scale space developments. So we started with my overview. We've had some observations from Dr. Diaz, and we're going to be following with discussions, I believe after lunch, on topics as disparate as nuclear thermal propulsion and the use of the resources of the small bodies of our solar system. Jim Powell is probably one of the grandest thinkers that you never heard of. By way of introduction, I chose this one photograph, which captures a lot of Jim's career. He was for many years the director of the nuclear division at the Brookhaven National Laboratory. In this image, Jim is shown with Gordon Danby. As I recall the story, hearing it from Jim many, many years ago, he and Gordon were stuck in traffic and were thinking there must be a better way. And this was circa, as I believe, 1963. And as a consequence, the two of them came up with the idea of superconducting magnetic levitation, maglev trains. And here they are receiving, it looks like an Oscar, but I don't believe it's an Oscar, an award for the invention of maglev. And this, of course, led ultimately and briefly in the U.S. to the National Maglev Initiative as the underpinnings of what is now being done with the Hyperloop activity and resulted in the only working superconducting maglev system, which is in Japan. Truly a big idea to come from a snarl in the traffic. John, would you care to say anything with regard to introductory with regard to Jim? You've been a very close friend of his for many years.
Thank you, John. I am editing this into the video of the meeting because I want to present one thing here that's very pertinent, and that is this video from Japan Rail that was provided to me in 2003, showing how far the development of superconducting maglev had progressed even 15 years ago. Jim Powell's invention was realized by the Japanese, and now they're moving forward at flank speed to expedite it. It is the fastest ground transportation in the world, and it routinely achieves 600 kilometers per hour. Let's show this 2-minute video and then return to John's talk.
In December 2003, the superconducting maglev set a new world record in the railway industry with a manned speed of 581 kilometers per hour at the Yamanashi maglev test line. Running tests on the 18.4 kilometer priority section of the Yamanashi maglev test line were begun in March 1997. The superconducting maglev produces far less noise and ground-borne vibration than conventional high-speed trains. And since the maglev runs by levitation 10 centimeters above the U-shaped guideway, it has a high level of safety in the face of earthquakes at high speeds. These characteristics make the maglev an ideal solution for the large volume, high-speed transportation needs of tomorrow. The superconducting maglev is superior in its ability for acceleration and deceleration. It can accelerate to a speed of 500 kilometers per hour in only 5.7 kilometers, while Shanghai's Transrapid requires 17.8 kilometers to reach the same speed. The superconducting maglev would cut the journey time between Tokyo and Osaka to about 1 hour and carry 1,000 passengers. With 10 trains each way per hour, or 200 round trips per day, the trains will be able to carry 200,000 passengers daily. In March 2005, the Maglev Technological Practicality Evaluation Committee, under the Japanese Ministry of Land Infrastructure and Transport, declared that all the necessary technologies of the superconducting maglev for future commercial services have been established. The maglev has recorded a total test run distance of more than 600,000 kilometers, which corresponds to 15 complete journeys around the Earth. After extending the test line to 42.8 kilometers, we will implement tests to confirm the practicality of the superconducting maglev.
Okay, that should have made believers of anybody who wonders if superconducting maglev is just blowing smoke or is real. And John now will tell you just how real it can be for the power of synergy motives of this whole symposium.
So Jim offered some thoughts to this event, which I typed up, and then sort of riffled them together with some other slides that were available. So I apologize for the changing format. But Jim offers to our consideration this week his view that there are 3 key technologies that are required to explore and then later settle the solar system. First, a fundamentally new system for space launch that can launch supplies into space from Earth at dramatically lower cost than chemical rockets. And that includes not just expendable launch vehicles, but also reusable ones. The need to develop non-chemical rocket systems to enable much shorter trip times into the outer planets, moons, and asteroids with more payload capacity, and in particular, the capability for in-space refueling at the destinations. And the need for the technologies to extract and use the resources of the solar system, especially for refueling. Each of these in turn, with most of the emphasis on the first 2. So that's a typo. It should be 100,000 years ago. A few thousands of humans left Africa and spread across the world, requiring, of course, centuries for that migration to occur, but with life support, basically supplies, water, air, all abundant everywhere that they went. Today we have, it's actually 7.6 billion people on the Earth, and we aspire to moving out into space where the environment is quite harsh and you have to do a lot to survive. We have some 6 people on the station. It's cost so far something like $200 billion, and about $8 million per person day, which is a stupendously high number, and something like $40 million, although I think the Russians have actually raised that more recently, to go to the station. Similarly, if you use conventional rocketry, it's going to end up being much more than $8 million per person day on the moon. The similar observation is like $1 million per robot day for Curiosity. And so many tens of billions of dollars for a relatively modest colony on the moon or Mars, even if it were to be only 10% of the cost of the space station. Jim invented a thing called Tram, which is an application of superconducting maglev for the purpose of achieving very, very low cost, all electromagnetic launch into space. So there are really only 2 technical options, and this is off the Jim script, that give you the potential to do this. One, of course, is space elevators. Space elevators are very well known, and people talk about them all the time. And then there's Tram. And since I'm quite familiar with them both, and I was one of the first sponsors at NASA headquarters to fund work on space elevators, I will tell you, and I have many, many good friends who believe in them passionately. In my opinion, Tram is infinitely more feasible. So Tram, as a concept, it would magnetically levitate and accelerate vehicles with payloads to quite high velocities, with the electromagnetic acceleration taking place underground, and then the spacecraft and its payload ascending, as you'll see in a moment, and leaving Earth's atmosphere. So it's a maglev version of a concept which other people have talked about, like light gas guns or coil guns and so on. Gas guns or coil guns, those alternatives has exceptionally huge accelerations in there. It's inherent in the nature of the concept. The really fundamental idea with Tram is that it allows you at full scale to launch both people and cargoes, and not just highly robust slugs of matter that can stand 30,000 Gs. So it's really quite an important opportunity. So the energy cost, something like $1 a kilogram to go to orbital speeds. And then the fully amortized cost is something like $200 per kilogram, including the operations and maintenance. And from my perspective, one of the more remarkable things is that this technology would not only accelerate payloads to low Earth orbit, but also to higher orbits. And so it really is it could launch payloads directly to interplanetary trajectories from the Earth's surface, which is really quite remarkable. So there's a couple of different generations. One would just launch with something like 30 Gs payloads. They would be released into the atmosphere at a relatively low altitude, and then they would have to endure the shock and so on. So you need a very good aerodynamic ablation system and so on. But you have this starter kit would be, as I recall, a few tens of kilometers long and a few tens of billions of dollars. The full scale, which would then be 3 Gs of acceleration, would release payloads at very high altitudes on the order of 20 miles, on the order of 30 kilometers, so very similar to the thin atmosphere where the U-2 flies. You'd have the acceleration taking place while the track was underground, and then you would have an evacuated tube magnetically suspended through which the vehicle and its payload would ascend to its release point some 20 miles up. And these sketches just show you what it would look like. This is a tension-loaded structure, not a compression-loaded structure, so it's not like a tall tower concept or something like that. Rather, there are magnetic loops, both on the ground and associated with the tube, superconducting magnetic loops, and these basically want to thrust the tube away from the Earth, and then it's being held down by the cables. So it's a reverse suspension structure. And then the vehicle and its payload are released at high altitude. And the concept, of course, would involve a very substantial aircraft-like operation, and would have the potential, again, something like $1 a kilogram for electricity. The amortized cost, depending on how you defray those expenses, something like $100 a kilogram, with the potential to launch hundreds of thousands of tons per year, including people at basically lower cost than any other option, including the reusable rocket cases. And there are locations in the US, in Russia, of course, in China, and in Europe where there could be launch sites for Tram. The technology base largely derives from the technology of superconducting maglev that's been in development now for 50 years, far more mature than the technologies for Apollo when the Apollo program got started. There is an existing system being developed in Japan. As I mentioned, Hyperloop is a related development. And I'll leave that be. The second topic that I wanted to highlight, that Jim wanted to highlight especially, it has to do with the need for new types of rocketry. And so in particular, as Jim observes, that chemical rockets are today quite limited, with trip times on the order of a year to Mars using this technology. If you just had resupply from Earth using chemical rockets, the cost becomes stupendously expensive. And similarly, if you're trying to go beyond Mars to explore the asteroids or the moons of the outer planets, that also becomes, Jim says it's impossible. I think with in-space refueling, there are some other tricks that you could try to use to get chemical rockets to be far more effective. But Jim's argument is that it's really impossible. You need much higher specific impulse systems. Another of Jim's inventions is the particle bed nuclear reactor nuclear thermal propulsion system, which we'll be hearing more about in several different nuclear thermal propulsion in several different speakers over the next couple of days. But here again, Jim was the inventor of this idea, just like he was the co-inventor of maglev, and really made a great contribution to the field of nuclear thermal rocketry. These are just some photos of some small models of a particle bed reactor nuclear propulsion system modules snapped last night in John Rather's study. Jim also offered a couple of observations about Vasimir, which we'll be hearing more about, I think, tomorrow. I think it's tomorrow. And in any event, Jim's feelings are, one, that it's got some very attractive features. These are plasma systems of the sort that Franklin Chang Diaz, Dr. Diaz was speaking of a moment ago. Very high specific impulse, and they could be used, therefore, for exploring interstellar space, the Kuiper Belt, and so on. But, of course, Vasimir rockets cannot land on even small bodies using the Vasimir propulsion system because the thrusts are too low, masses are too high. They have very high power requirements. And, of course, they can't fly in planetary atmospheres because they're very non-aerodynamic. And then, in closing, the third of the three technologies that Jim offered his thoughts on are basically the resource extraction and utilization. And there's a particular innovation that Jim came up with called MIC, which is magnetically inflated cable. And I apologize, I ran out of time to dig out some images of MIC from the web, and it would have interfered with Dr. Diaz's video link. But nevertheless, I think we're going to be hearing a lot about this in just a few minutes after the lunch break from Joel Sercel, who has spent a great deal of time and effort thinking about how best to pursue space resources. And then Jim also included just a couple of thoughts about the search for life in the solar system. So the three areas, just to summarize, that Jim thinks are of profound importance are extremely low-cost launch, i.e. all electromagnetic launch, fundamentally higher efficiency and higher lower trip time in-space propulsion, and the need for the development of the resources of the solar system. And I think those are topics of pretty common acceptance. The one where I think Jim is still perhaps a bit ahead of its time is in the use of maglev for launch from Earth. But I will just mention that another application of these technologies other than high-speed rail systems is, of course, for launch from surfaces such as that of the moon, where it is so much easier to launch. So Maglev may get its first opportunity to launch for dollars a kilogram in the other planetary settings than from the Earth. And with that, I will stop. Thank you.